Friends, where are the hydrogen cars? 10 years ago, fuel cells and hydrogen cars seemed like a sure future. Today, the dream seems dead. In Japan, Toyota has remained one of the few players still betting on hydrogen cars. Look at this chart. Electric cars are on the left. Their growth is massive. On the right are the hydrogen cars. You don't see anything on the chart. Look carefully at the bottom right. There are so few that you can't even see them on the chart. There are many reasons for this failure. The most important thing remains the technology. I talked about hydrogen technology in the previous video. Those of you who saw that video will know that, compared to electric cars, which take in electric energy directly and transmit it to the motor, hydrogen cars require two additional intermediate steps. The first step is the electrolyzer, which is located in the factory and transfers the electric energy from the outlet into the chemical energy of hydrogen. The second step is the fuel cell, which is found in the car and converts the chemical energy of hydrogen back into electric energy in order to rotate the shaft of the electric motor. Two intermediate steps that cost money and in which additional energy is lost. Look, let's say we have industrial electrolyzers, which convert the electric energy from wind turbines and photovoltaic solar panels into the chemical energy of green hydrogen, separated from water. Then, we compress the hydrogen and store it in tanks and transport it to fueling stations for cars, or we transport it there through a dedicated hydrogen pipeline network, an infrastructure that still doesn't exist. At the fueling stations, the hydrogen is loaded into the car's tank. The energy density per kilogram of hydrogen is much higher than that of electric batteries. 33,000 W-key of hydrogen compared to only a few hundred W-key for lithium-ion batteries. The same thing happens with energy density per volume. With higher energy density, hydrogen has an advantage. We fill the tank with more energy and it goes farther than the electric car. Plus, we can refuel with hydrogen faster than we can charge an electric battery. But if we remember the explosion of the airship Hindenburg, which had hydrogen in its balloon, maybe we're scared to carry compressed hydrogen tanks in the car. However, it seems that they are very safe as long as the regulations are followed. Researcher Michael Swain from the University of Miami says that they are actually even safer than the gasoline in a regular car, which is also flammable. In the hydrogen car engine, we need something else: fuel cells. These operate in the opposite way to electrolysis. The hydrogen from the tank is combined with oxygen from the air to form water. There's also water vapor coming out of the exhaust pipe, which is ideal for a clean environment. During the process, the chemical energy stored in the hydrogen is released, which was stored when it was extracted from water. The cycle is complete. When we extracted hydrogen from water through electrolysis, we used electrical energy from the outlet, let's say produced by wind turbines, to store it in hydrogen. Now we have recombined the hydrogen with oxygen, recovering the initial water and releasing the chemical energy of the hydrogen, which we converted into mechanical energy through fuel cells and the electric motor. The overall efficiency of the process, less than 40%, some even say 30%. Yes, you heard that right. That's compared to an electric car, which has an efficiency that even exceeds 80%. Extremely little when it comes to hydrogen. This is also reflected in the cost. Estimates show that the energy cost per kilometer for hydrogen cars is about 3 to 4 times higher than for battery electric cars, although I have found estimates that say it is more than 10 times higher. That's why there are many voices saying that it doesn't make sense to bother with hydrogen to power cars. We lose too much energy along the way, almost 60 to 70%. And only 30 to 40% remains. The cost will automatically be higher than for an electric car. Why is so much energy lost with hydrogen compared to the electric car? It's normal. With the electric car, the energy is stored directly in the battery without conversion like with hydrogen, where electrolysis is used. And it's used directly from the battery without another conversion like in the fuel cell. This approach removes the entire energy-losing chain seen with hydrogen from the beginning. This is the main reason why, in practice, we still don't have hydrogen cars. Only a few models of such cars are produced in the world, like Toyota Mirai or Hyundai. Nexo. And in Germany, the strongest European economy, only 263 new hydrogen cars were registered in 2023, down by 70 compared to the previous year. Simply put, hydrogen technology is more complex. With additional elements like electrolyzers and fuel cells, the efficiency is still low and the hydrogen distribution system is almost completely lacking. Let's be honest, it seems like a dead end for cars. Mobile. The energy efficiency of hydrogen cars is much lower than that of electric cars. The efficiency is somewhere between 30 and 40%. So, is hydrogen completely useless for transportation? Not necessarily. Electric transportation has a problem today, the weight and volume of batteries. We see this from the very small number of electric cars that can go over 400 kilometers without being recharged. Of course, you can go 800 kilometers on batteries if you carry twice as many batteries with you, but that means double the battery cost as well as double the weight and volume. For trucks, the numbers will be even higher. If we talk only about trucks, there are some immediate advantages to hydrogen. The energy density of hydrogen is higher, both in terms of volume and mass. This means that a hydrogen truck will have a greater range than a battery-powered one. The same volume or mass. In addition, hydrogen can be refueled much faster than a battery can be charged, and that's important for trucks. That's what we see in this chart. It's a prediction of the types of trucks that could exist in the year 2050. As you can see, most of them would be electric when the distance is less than 500 kilometers. For longer distances, however, the trucks could run on hydrogen. Hydrogen is still less efficient than electric batteries. That's because someone somewhere will be willing to pay more to transport faster with hydrogen and over longer distances. It's possible this scenario won't occur by 2050. That's because electric batteries are developing rapidly now, and it's possible that in over 25 years the energy density in electric batteries will increase, thus cancelling out hydrogen's advantage. It's true, there have been a few hydrogen truck projects. However, none of them are economically feasible yet. Another type of project is the Hyundai Zint fuel cell, a hydrogen truck launched by Hyundai. Although it promises extended range and zero emissions, the high production costs and limited infrastructure for hydrogen refueling make it difficult to adopt this type of vehicle on a large scale, at least for now. Along the same lines, there is talk about hydrogen ships such as Energy Observer 2, which is expected to be put into use in 2025. Or about hydrogen-powered airplanes, with the first one expected to be built by Airbus in 2035. But are these processes economically feasible? I'll let you write in the comments based on what we've discussed above. One area where it was hoped that hydrogen could play a role was in residential and commercial heating. Here, hydrogen would have replaced natural gas, either by blending it into the existing adapted gas network or by completely converting gas systems to hydrogen. The goal would have been to reduce carbon emissions. However, it seems that this will not happen, at least not in the near future. On one hand, hydrogen is a small molecule and escapes through cracks. Sealing the existing gas pipeline would be expensive. Building new ones would be even more costly. In addition, according to the EPG report, a combination of 80% natural gas and 20% hydrogen could lead to an increase of over 1/3 in the price of the resulting natural gas and implicitly in consumers' bills. At the same time, such an approach would be inefficient because almost half of the energy associated with this process would be lost. The 20% value is chosen to be low so that the existing gas distribution network can be used without too many modifications. Above this 20% threshold, significant modifications would be necessary for various components. Because the maximum concentration of hydrogen in natural gas pipelines is significantly affected by pressure fluctuations, structure, and existing defects. In addition, another report, the one from Ben Kwok, states that, in terms of safety, hydrogen is 7 times more flammable than fossil fuels and burns at a higher temperature. Enhanced safety measures would be needed for domestic use. The situation becomes even clearer if we compare green hydrogen heating with heating using heat pumps. Take a look at this study. On the left, there are 100 kW of electricity obtained from renewable sources. We pass the energy through electrolysis, extract hydrogen, transport it through pipelines, and put it into a boiler, and then we're left with only 61 kWh of useful energy. On the right, we see how much we get from the heat pump if we put the same initial 100 kW into it. 270 kW, which is almost 4.5 times more than from hydrogen. If you're surprised that more energy is obtained, please watch my video about heat pumps. The heat pump is clearly much more advantageous. For all hydrogen systems, transportation is a problem. For short distances, transporting hydrogen through natural gas pipelines would be the preferred option, but it's not that easy. Here's what the EPG report says. For distances less than 1,500 km, transporting hydrogen through natural gas pipelines is generally the least expensive option. Although this requires either reusing existing infrastructure or new investments to connect production sources to demand points. For longer distances, transporting hydrogen as ammonia or as a liquid hydrogen carrier could be a relatively rare option, but conversions come with significant efficiency losses. If you didn't know, in Romania we have a draft national hydrogen strategy, which is currently going through the environmental approval stage before adoption. Essentially, it's a requirement from the European Union because part of the funding will also come from there. To give us an idea, the current situation looks like this. At present, the grey hydrogen produced in Romania is over 200,000 tons, and the green hydrogen produced by electrolysis is only 3,000 tons. That means we need an almost 60-fold increase in green hydrogen to replace the industrial grey hydrogen. The draft National Hydrogen Strategy estimates an investment requirement of 4.8 billion euros to produce 150,000 tons of hydrogen per year from renewable sources by 2030. Of that, 47 would be used in transportation, 37 in existing industrial activity, and 15 in new industrial applications, specifically in steelmaking. Simply put, by the year 2030, about a quarter of the grey hydrogen produced in Romania would be converted into green hydrogen. If I divide the 4.8 billion euros by 6 years until 2030, I get 800 million euros per year. If I further divide that by the 150,000 tons of green hydrogen produced annually, I get a subsidy of almost 5 euros per kilogram of green hydrogen produced each year. Essentially, I can't help but notice that this is the current market price of green hydrogen. Although the subsidy is not dedicated exclusively to industrial users of hydrogen, it is mainly intended to increase the production capacity of green hydrogen. Because in order to generate this green hydrogen, Romania needs electrolyzers and additional solar panels, and eventually wind power plants. In principle, the energy could also come from hydropower or nuclear plants. It is estimated that in order to meet the demand for green hydrogen, 4,000 megawatts of dedicated installed capacity from solar and wind energy are needed. These are very large numbers. Assuming Romania has 1,500 megawatts of installed photovoltaic capacity. Photovoltaic, in addition to those visible in the national energy system, Romania had installed at the prosumer level, as of June 1, 2024, another 1,780 megawatts. Basically, the photovoltaic capacity should almost double by 2030 in order to generate green hydrogen. That's not a small amount. Romania's ambitions are big here anyway. In the draft of the Integrated National Plan for Energy and Climate Change sent to the Commission, Romania is aiming in 2030 for 8,300 megawatts installed in photovoltaic panels and 7,600 megawatts in wind turbines, without taking into account the additional requirement needed for hydrogen production. When it comes to electrolyzers, the draft National Hydrogen Strategy anticipates an installed electrolysis capacity of 2,000 megawatts. Romania currently has a much lower capacity. Currently, there is only one PNRD scheme to support the development of a 100 megawatt electrolysis capacity. Recently, OMV Petrom obtained funding for 2 electrolysis plants with a total capacity of 55 megawatts. What surprises me in Romania's strategy is not the support given to the industry to produce and use green hydrogen instead of grey hydrogen. That is a long-term requirement of the European Union, but rather the very large allocation of green hydrogen for transport. However, I assume that these percentages also refer to the hydrogen used in the oil refining process, meaning industry. Basically, a large part of the 47% will contribute to oil refining and another part to the production of synthetic fuels for aviation and shipping. Increasing photovoltaic capacity to produce green hydrogen could also be a problem in itself because it will raise questions in society. But people will wonder why. If so much photovoltaic capacity is being installed, wouldn't it be better to use this electricity directly to turn on the lights or charge the electric car? Of course, people overlook the fact that most of this capacity is being built to convert existing gray hydrogen into green hydrogen. I'll be honest with you, when I started my research for this series, I was skeptical about green hydrogen. I knew about the low energy efficiency of hydrogen cars, which is only about 30 to 40% throughout the chain, compared with efficiencies above 80%. And I also knew that hydrogen is not an energy source. It transfers energy from one place to another. Simply put, hydrogen does not replace fossil fuels. It's still photovoltaic panels, wind power plants, and hydroelectric plants that will do that. Hydrogen only transports energy from one place to another and from one moment in time to another. In other words, I knew that hydrogen is not a miracle solution to the problem of global warming. That was confirmed by what I read. As I anticipated, using hydrogen in road transport remains economically inefficient. If we replace gasoline and diesel cars, they will most likely become electric cars, not hydrogen-powered ones. On the other hand, I have discovered the importance of hydrogen in industrial processes. Because reforming methane to produce gray hydrogen makes a non-negligible contribution to global warming. 2%. In other words, if the European Union is serious about its goal of achieving climate neutrality by 2050, it must replace this gray hydrogen with green hydrogen with much lower carbon emissions. We then need electrolyzers, photovoltaic panels, and everything else. However, this is a decision society as a whole must make. I'll stop here with the technical aspects of the problem that I tried to clarify for you. Until next time. Please subscribe if you haven't already by pressing the subscribe button right now. I want to thank those who support me on Patreon and those who become channel members here. I'm Christian Pressure from Physics Explained. You guys are cool and I wish you all the best. Goodbye.